Right, welcome to lesson 2 of the grade 8 chapter on whole numbers. So let's just look at a few kind of estimation and calculation tricks. The first thing is estimating is a really valuable skill. So if we were going to multiply 199 by 21, this number is quite close to 200, and this number is quite close to 20. So we could, in fact, just multiply 20 by 200, which gives us 4,000. It's not exact, but it gives us a sense of the size of the number. Right, let's now look at how we would calculate this as we've been taught before with kind of long multiplication. And then let's just take a minute to understand why that works. All right, so what we do is we put the bigger number here, 199 times 21. All right, what we do now is we multiply 199 by 1, by this 1 over here. All right, and what we get, in fact, we get, obviously, 199. That was pretty easy. Right, the next thing we're going to do is we're going to multiply it by 2, but in fact it's not by 2, it's actually by 20. And if we're going to multiply it by 2 and by 20, we could just multiply it by 10 and by 2. So what we do is we put a 0 here, all right, and that is the multiplying by 10. Then we multiply the 199 by 2, and what we get is we get 8, 2 lots of 9, 18, carry 1. 2 lots of 9 is actually 18, plus the 1 we carried is 19, and then we carry 2 lots of 1, and we're still carrying 1, so 3980, and now we add these two together, and what we get is we get 4179, all right? We actually add them from here, and we have carries out, but hopefully you're okay with that. Right, just again, to understand why that actually works, what we're doing is we're multiplying 199 by 21. But in fact, that is 199 by 20 plus 1. And we know from the distributive law of mathematics that this 199 needs to multiply by 20, and it needs to multiply by 1. All right, so in fact, we get 199 times 20 plus 199 times 1. Right, and this piece, 199 times 1, is in fact that piece. And this piece, the 199 times 20, is in fact that piece. Okay, right. Let's now look at another way of doing this question, all right? 199 is actually quite close to 200. So if we've got 199 lots of 21, what we could do is take 200 lots of 21 minus 21. Right, now 200 lots of 21 is, we could write that like this. Notice how we've associated the 2 with 100 and the 21. Now we've changed it to 2 times 21 because that's easy to calculate. So we end up with 42 lots of 100 minus 21. And that's maybe an easier way of doing it than the long multiplication. Let's just try doing some of these like this. So if we had 99 times 57, that's just going to be 100 lots of 57 minus 1 lot of 57. Right? So it's actually going to be 5,700 minus 57, which is indeed going to be 5643. Okay, maybe you try the next one, but let's have a look at it. Pause the video and then try it and then have a look. This is going to be 100 lots of 43 plus 1 extra lot of 43. So what we're going to get, 4,300 plus 43. All right, and that simplifies quite nicely to 4343. Let's do 999 times 67. Well, that's clearly 1,000 lots of 67 minus 1 lot of 67. So it's going to be 67,000 minus 67. In fact, it's going to be 66933. Okay. 50 times 99. Well, that's going to be 50 times 100. Right? Sorry. 50 times 100 50 lots of 100, or 100 lots of 50. Let's actually rather write it like this. It's going to be 100 lots of 50 minus 1 lot of 50. This is 5,000 minus 50, and we get 4,950. Right, 27 times 101. Well, that's pretty straightforward. It's 100 lots of 27. That's one more lot of 27. That's 101 lots of 27. We get 2,700 plus 27, and we get 2,727. Okay, 48 times 1,001. Well, that's pretty straightforward. It's 1,000 lots of 48 plus one more lot of 48. So it's actually going to be 48,000 plus 48. Just something I want to draw your attention to. Notice we are always working downwards. We're always writing out the whole sum, right? In other words, we're not being lazy and leaving out this plus 48. And we're always writing an equal sign. And if we left out the plus 48, then our equal sign would in fact not be correct, okay? We're keeping the same value as we had on the line above. And then the last thing that I kind of really like that we do is that we just underline our answer with a little arrow. Okay, it just makes it clear that we've finished that sum. Okay, right, there's space to make up some extra examples here. And then let's move on to looking at how do storekeepers manage to give you your change so easily. Well, the thing is that they actually don't do subtraction, right? Suppose you pay 13 Rand 68 for something and you pay with a 20 Rand note. In fact, what the person behind the counter does, they don't calculate the change. They actually just add back up. So, for example, they will need to give you a 2-cent piece to make you up to 13 Rand 70. Then they will need to give you 30 cents to make it up to 14 Rand. And then they'll need to give you 6 Rand to make that up to 20 Rand. So all those bits add up to the difference. So in fact, 20 Rand minus 13 Rand 68 is actually 6 Rand 32. Right. It's typically much easier to do it like that than to do it by subtracting. So for example, let's just look at some examples. If we had 500 minus 297, I would need 3 to make it up to 300, and then I'd need 200 to make it up to 500. So in fact, the answer is 203. Right, with this one, I would need 13 to make it up to 300, and then I need another 50. So the answer would be 63. Let's look at this one. I would need 25 to get to 400, and then another 80. So 25 plus 80, 105. Right, and then lastly, over here, I would need 63. So I need 3. Let's do it slowly. I need 3 to get to 140. I would need 60 to get to 200. And I need another 50 to get to 250. So if we add all these up, we get 113. Okay. Once again, there's some space there for your teacher to make up some extra examples. We're now going to look at prime numbers, right? And we're going to firstly establish which are the prime numbers between 1 and 100 using this thing called the sieve of Eratosthenes. So what we're going to do, we're going to follow the directions below here, which ask us to shade out 1, all right? Then to shade out all multiples of 2 apart from 2, all right? So if we look, all these numbers over here are even, okay? So they can actually go. Next up, we're going to shade out all multiples of 3 apart from 3. So there we go, 9. Next up, we're going to shade out all the multiples of 5 except 5 itself. Well, the multiples of 5 are the multiples of 10, which are already gone, but it's going to be these ones here. And then lastly, we're going to show down all the multiples of 7 apart from 7 itself, right? And those are, in fact, 49 needs to go. So does 77. And so does 91. Okay, I'm just going to take a minute to check that. And I think we've now got only our prime numbers remaining. Indeed. All the numbers that are left here now are the prime numbers. Okay, that's called the sieve of Eratosthenes. Right, let's write them down. All right, and in fact they are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97. Right, let's just count them. The next question is how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Bingo, there are 25. I happen to know that there are 25. So thankfully we haven't left any out. There are only 2 prime numbers which are consecutive, all right, one after the other. Okay, they're what we call, right, let's have a look. The only 2 are 2 and 3. Why could there not be another pair of consecutive prime numbers? Well, the thing is that every other pair of consecutive numbers will have an even number, all right? Each consecutive pair so 2 numbers that follow on from one another will contain an even number. It will either be an even number then an odd number or an odd number then an even number. And all even numbers apart from 2 are prime. So all even numbers are not prime. All even numbers apart from 2 are not prime. Okay, right. Twin primes are 2 primes which are 2 apart. And there's quite a lot of these. And the first pair of twin primes is 3 and 5. Let's see if we can write down the rest. All right, let's write down all of them. 3 and 5. 5 and 7. 11 and 13. Notice these are all odd numbers. 17 and 19 are both prime. They are twin primes. They are just 2 apart. 29 and 31. 41 and 43. 59 and 61. 71 and 73. Right. Do you think that primes become more common or rarer as the numbers get bigger? Well, I can tell you that they actually become rarer, become less and less common. All right, rarer, less common. Let's write it like that. Less common, less frequent. All right, so we get fewer and fewer as the numbers get bigger. And the reason why is as the numbers get bigger, there are more and more possible factors, more and more numbers that could go into them and make them non-prime, more and more possible factors. Okay, do you think there's a biggest prime and why? Well, in fact, there's none. No, there isn't one. All right. I'm, in fact, not entirely sure why. All right. Maybe if there was one, we would know. All right. So maybe if there was one, we would know it. Right. Euclid, who lived around 300 years BC, proved that there is no biggest prime. They get rarer and rarer, less and less common, but in fact, there's no biggest prime. Okay, and then, yeah, big prime numbers have got quite a lot of application, all right? The biggest one that we know of so far has, if we go and look on Wikipedia, it actually has 24 billion, 24 million, 862,048 digits. Right, if we wrote them down one per second, all right, it would obviously take us that many seconds to write the number down. If we divide that by 60, we actually get 414,367 minutes. Right? And if we divide by 60 again, we get 8,125 hours. And if we divide by 24, we get 288 days. Right, so if we wrote this number down, this biggest prime number, with that many digits, all right, that's how many digits it's got, and we wrote them down one per second, right, for 24 hours a day, no sleeping, it would still take us 288 days to write down. It's an enormous number. Right, quite a fun game is this prime game, right? Play it and see who can get the highest score. And that's just testing whether you can correctly identify which numbers between 1 and 100 are prime and which ones are not. Next up, we're going to look at what is called Goldbach's conjecture, right? And what he said is he said that any even number greater than 2 can always be written as the sum of two prime numbers. So, for example, 12, we can write as two prime numbers added together. Okay, let's see if we can do these using only prime numbers, only two of them, and adding them together, right? We've already done 12. 12 is 5 plus 7. There are no other options for 12. You might say, what about 3 plus 9? 3 is prime, but 9 isn't. Right, 10, 7 plus 3. There might be other options. For example, 10, we could also do 5 plus 5. Okay, two prime numbers that add together to give 10. 16, 3 plus 13. I can think of another one, and that's, no, I can't. No, in fact, I can. 20, 7 plus 13. Here I can think of another one, or 3 plus 17. Both of those are prime. 36, 29 plus 7. 42, 37 plus 5. In fact, 35 plus 7. No, 35 plus 7 will not work. 35 is not prime. 37 plus 5. 48, 5 plus 43. 70, 11 plus 59. But possibly also 67 plus 3. 82, 79 plus 3. And 94, maybe not such an easy one to do, but 71 plus 23. Right, this conjecture that every even number bigger than 2 can be expressed as a sum of two prime numbers has never been proved, all right? But equally, nobody's ever managed to come up with an even number that they couldn't express as a sum of two prime numbers, right? So if you could find one, then you'd be mathematically famous, all right? Numbers that have no common factors are said to be relatively prime, right? So for example, 8 and 21 are relatively prime. There's nothing that goes into both of them apart from 1. They're not prime numbers themselves. Right, now this has an important sort of tie-in with when we simplify a fraction, for example, 48 over 60, if we divide both the top and the bottom by 12, we get 4 over 5. When a fraction is in its simplest form, the numerator and the denominator are relatively prime. They're not necessarily prime, but they share no common factors. Right, give 3 numbers which are relatively prime. So for example, 11 and 12 and 35. Those 3 numbers are relatively prime. Are 54 and 3000 relatively prime? No. All right. Why are they not? They have a common factor of 2. They might have other common factors as well, but they certainly have at least one common factor other than 1. They have a common factor of 2. Okay, and that brings us to the end of lesson 2 of whole numbers.